Hello everyone. So a couple of years ago I inherited a spectrometer, this thing here. I'll explain what it is in a moment. I inherited it from my PhD supervisor, Professor Ted Milton, who unfortunately died a couple of years ago, and I got a lot of his scientific kit. So I'm going to use that today to point it at various things, look at how light works a bit, understand how light interacts with different surfaces and different substances, and then we can do a bit more playing in the Q&A tent afterwards. So first of all, before we go into that, we need to think a bit about what light is. Now, light is part of the electromagnetic spectrum, which runs all the way from X-rays and gamma rays over to radio waves. Light's kind of in the middle, and the visible light we can see ranges from violet and blue through to red. And you can measure the wavelength of this light in nanometers, so from 400 to about 800 nanometers. Either side, you've got some bits of the spectrum that we can't quite see. So you can't quite see ultraviolet light, and you can't quite see infrared light. They're on the either end, beyond the violet or beyond the red. But the spectrometer can, and we can switch here to a display from the spectrometer. So what we've got here is on the x-axis, we've got the wavelength. So this is the wavelength of light running from about 350 to 850. We can put a few colours in the background here to get an idea as to what's going on with the colours here. So blue is that blue area on the left there, then we go through green and yellow, marked out as green there, and then through into orange and red, marked in red here, and then this region here is the near infrared, which I've marked in purple. And then you can see a graph on the screen. The y-axis is the intensity of light, so the brightness of light at that wavelength. So the higher it is on the y-axis, the more light of that wavelength or that colour there is. Now, can we have the main stage lights down if there are any stage lights on? Maybe there aren't at the moment. They're all off. Okay, in that case, the light that we're seeing, the spikes we're seeing in this spectrum here, we won't be able to do much about today. They're from the actual projector, which we can't turn off. But we'll look at the overall shape of what's going on, and actually we can do a higher intensity version of this. So here we're looking at an incandescent bulb. These are the now quite old-fashioned types of bulbs that were very, very common up until about the 2000s. They make light by just getting something really, really hot, and it glows white hot. They've got gas in the bulb, but the gas in the bulb is just to stop the filament burning up. It doesn't actually produce any light itself. And what we see here in the spectrum is a fairly gentle curve, peaking in the green and the red, with a bit of blue, a bit of near infrared, and a generally fairly sort of overall kind of curvy kind of shape. Now, if we change this to have a look at a different sort of light, this is a compact fluorescent light. So this is like a fluorescent tube, but it's twisted so it fits in a normal light bulb socket. And, whoops, if we look at this, let's switch back. Here we are. This is the spectrum. Let's just hold that so I can put this down. This is the spectrum we see. So you see it's very, very different to an incandescent bulb. There are big peaks and spikes in the spectrum and big areas where there's almost no light at all. That's why things often look weird under fluorescent lamps, because there's whole areas kind of here and further along where you just can't get any reflectance from anything because you've got no light coming out of the light bulb. The way this works is that you put high voltage through some gas in there. That produces actually ultraviolet light, which then hits a fluorescent coating on the inside of the bulb, which absorbs that ultraviolet light and releases it again as visible light in various different wavelengths. And we can actually see how this works with this ultraviolet torch I've got here. So if we, oh dear, there we are, it's working, good. If we turn this ultraviolet torch on, you can see we're getting a peak here, the other side of blue, so into the ultraviolet part of the spectrum. And I've then got some fluorescent paint here that I borrowed from my son's science kit, thank you Julian, and I can point the ultraviolet light at this fluorescent paint, and we can see what we've got here. You can see the ultraviolet peak around 400 nanometers, and some of that ultraviolet light is being absorbed by the paint. It excites the atoms to make them at a higher energy level. They then relax again and release light at a longer wavelength, a higher wavelength, and you get this peak in the orange part of the spectrum. And that's how the fluorescent coating of the fluorescent lamp is working. Nowadays, though, you probably have LED bulbs in a lot of your places in your house. This is what the spectrum from an LED bulb looks like. Let's just get that a bit better, and then we'll take a, whoops, there we are. Take a spectrum of that. So this is a better sort of light than a fluorescent lamp for colour reproduction, because you've got a broader range of wavelengths, but you have got these big peaks at certain wavelengths. That's because the way these lights work is you have a blue LED releasing blue light, which then hits a fluorescent or phosphorescent pad above it, which releases light at other wavelengths. The phosphors are chosen to release light across a range of wavelengths, but they do get these spikes where you get peaks of light released at certain wavelengths. So it still looks a bit more unnatural compared to an incandescent bulb, but still a lot better than a compact fluorescent lamp. So before I demonstrate the next thing, I'm going to get out a little bit of kit called an integrating sphere. This is an integrating sphere. You may notice something about it. It's not spherical. It is actually spherical inside. It's got a spherical cavity inside it, but it's just cuboid, so I can sit it on the desk and it doesn't roll away, which is kind of useful. And what it is inside is this spherical cavity that has a white coating that reflects a lot of light really well. And so what happens, if you put light in one port of the spectrometer, whoops, you can't quite see that, you can see that, up here, it then bounces around the inside loads and loads and loads of times before coming out any of the output holes. And that means you get a lovely, lovely diffuse beam of light. So it's uniform light across the whole of this port. So if I look at this and point this at the ceiling, I get a very narrow laser beam. If I put it in here, this is probably the first time you've seen a diffuse laser beam. This is the laser light. You can't see it on the ceiling. You look up here at the spectrometer. At the integrating sphere. You should be able to see this glow inside, which is coming from the laser being bounced around. So we can then put the spectrometer somewhere and point the spectrometer at the hole and put the laser light in and see what a laser looks like, which is almost monochromatic. So this is very narrow wavelength. A laser light, because of the way it's created, is very narrow in its wavelength range. And we can look at one more thing while we've got the integrating sphere out, which is just a standard LED that you might use in an electronic circuit. This is my terrible soldering here with a red LED here. So, in fact, it's so terrible that I've just broken the LED connection. So we're not going to look at an LED, never mind. We might be able to see one. Yes, we can see one I prepared earlier in best Blue Peter fashion. So that's what a red LED looks like. So you've got a far wider wavelength range than you do for a laser, but still relatively narrow. Right, another way of producing light, sources of light, are things like your phone screens and your laptop screens. So they have light sources inside them. It varies depending on the exact display technology, how it works, but they do it by combining light of different wavelengths. So if we look at this, my phone at the moment is displaying a white screen, and you can see that we've got some blue light, some green light, and some red light, and we're combining those to make white light. If I make this screen go red, my screen is now red, you can see we just get the red light. If I make my screen go green, we just get the green light, or just the blue light. And if we start doing other colors, we get purple, for example, by combining red and blue like you'd expect. So if you actually look at how one of these screens works internally, this is actually my phone screen using a microscope. You can see when white is being displayed on the left there, you've got lots of red, green and blue lights all turned on. On the right there, you're just turning on the red lights inside the screen, and you're getting just a red display. So how do these spectrometers work? It's actually quite a little bit of kit I've got here. Still costs quite a lot of money, so I'm glad I inherited it, not bought it myself. professional, really good ones will be really chunky bits of kit, but they all work in the same way. You start off with a light source, which comes in by something like this, which is a fiber optic cable, and it goes through an entrance slit to get a narrow beam of light, and then goes to a grating. Now, a grating, in this sense, is a bit of plastic with a sort of grill on it, a grid of very small little bumps. This is a diffraction grating. You can come and have a play with it later. You might be able to just about see some rainbows on this while I'm moving it around. I can see a lot when I look at the projector light. That's what it's doing in there. A grating basically works the same way as a prism, but it's just a bit better. And so it splits light out into the rainbow, and the light is split out then onto a detector. And the detector is very much like the detector you have in a digital camera. It's a CCD, so it detects light falling on it, and you can use that to detect where the light is at different wavelengths. If we look here, this is the actual spectrometer I've got. You can see light comes, where's my pointer gone? Light comes in at the bottom here, bounces off there, goes through the grating here, bounces off there, and is spread out across the detector here. And the detector will have a long, narrow detector, and going across the length of the detector will be different wavelengths, because we've spread it out so that blue is at one end and red is at the other end, or in fact, ultraviolet is at one end and infrared is at the other end. And then going down the rows of the detector is basically just repeated data. We just average across those to deal with noise and so on. So if you were to look at the detector, when you pointed it at something like a fluorescent lamp again, you would see something like the top image here. You would see lots of black areas where there's no light, and then you would see the actual light in its colors at different points. And the spectrometer basically just measures the brightness of that and converts that kind of image into this kind of graph with the relevant wavelengths on it. So we've looked at light sources so far, but most things around us don't actually emit light. We can see them, light is coming from them, but they aren't producing light. They're reflecting light. And that's the way that most visible things work. If you look at a tree, which is green, the reason it looks green is because lots of light hits the tree, and the tree reflects green light towards your eyes, whereas it doesn't reflect as much red light or yellow light or blue light or whatever. So that's why a tree looks green, and we can do a similar little demonstration here. So I have some normal pieces of card here, just some green and red pieces of card. So let's experiment with those. We're going to turn on now a halogen lamp. It's got a very similar spectrum to a incandescent bulb, but it's just a bit brighter and a bit more stable, which makes life a bit easier. So here's our incandescent bulb, here's our red bit of card that we're pointing at, and we can see that if we point the spectrometer at the the halogen bulb, we get a spectrum across lots of wavelengths. If we point it at the red card, we are seeing mostly light in the red part of the spectrum. And if we then look at a green card, it looks relatively similar, but a peak in the green. Still quite a bit of light in the red, though, here, but a lot in the green. Now, there's something else going on with that, because what we're looking at here, it depends on what our light source is giving us. If our light source gives us lots of red light, even if this only reflects red a little bit, we'll still see lots of red light here. We need to somehow normalize this to what we can get from what we're actually getting from the light source. And this is where you bring in a very expensive piece of white plastic. This is a very expensive piece of white plastic. By very expensive, I mean multiple thousands of pounds. It's a Spectralon panel. This is a slightly damaged one, hence why I've brought it to a field. And it's basically really reflective in almost all wavelengths and reflects uniformly across wavelengths. So basically, it's pretty much perfectly reflective in all the different wavelengths and from all the different angles, and it's meant to stay stable over time. So if we put it here with our light there, if we point our spectrometer, whoops, come here. If we point our spectrometer at the light, we get, whoops, we're saturating there. we point our spectrometer at the light, we get the same pattern that we get if we point the spectrometer at the spectral panel. Ignore this extra peak here, that's the light from the projector getting reflected from the spectral panel as well. So we can use this to compensate for our the spectrum of our light. So if we take a reference spectrum here, what we're going to do is divide everything we measure from now on by this reference spectrum and say what proportion of the light coming from basically what proportion of the light source are we seeing. So if we capture our reference spectrum, you'll see here what we're seeing is all the values around 1. So at the moment we're basically seeing 100% of what we would see in every wavelength from the raw light source itself. But if we then put something like a green bit of card over here, we'll see we get this big peak in the green again, but the numbers on the y-axis down the side are reflectance. So they're the proportion of the light that is coming in here that is being reflected from whatever you've got under the spectrometer. So that's why you can see far lower red reflectance here, because although we've got more light coming in the red, a lower proportion of it is reflected. So we can move on to looking at some other things under the spectrometer using this spectral panel. So I went out just before this talk and picked some leaves from various plants. So let's have a look at a leaf under the spectrometer. So what we can see here, let's just average that out to make it a bit smoother. You can see we haven't got much reflectance in the blue. We've got a little bit more reflectance in the green. That's because the leaf looks green. And then we've got a lot of reflectance in the near infrared, this area of the infrared just on the top right here. And that's very typical for plants of any sort. Vegetation of any sort will have a really high near infrared reflectance and a fairly low blue and red reflectance. So we can do the same thing with another leaf. Whoops, that's a bad example. Let's just, whoops. Let's see whether we can get a leaf from this plant. I stole a plant from the greenhouse earlier by the lounge. Whoops. I think we've done our reference spectrum badly. Let's put that, there we go. So that's a brand new fresh leaf from a plant that is currently growing. You can see we get a lot higher green reflectance because it looks really green, it's growing really well, and we get this sky-high near-infrared reflectance. But you can also look at other things. So, for example, here is some soil. So soil has a very low reflectance, it looks dark, that's why it has a low reflectance. Snow, on the other hand, has a very high reflectance. I haven't got any snow here today, can't think why. But also, you can look at how things change over time. So here's my soil, I'm now going to put some water on it, and it gets even lower reflectance. Soil gets darker as you put water on it, same with sand. So you can look at, there's quite a lot of changes that happen to the spectra there. There's also, here's a lump of, this is sort of tarmac-y stuff that I stole from the side of a road somewhere. And you can look at it, and again, it's quite a dark reflectance, but there's a few other more interesting features here, a few little peaks and a few little troughs going on in the chemistry of the tarmac. So, I'm going to switch now from talking about stuff that I've done here to stuff that happens in space, but don't worry, there is a really big link. And this is an example of a satellite that takes images of the Earth. This is Landsat 8. It was launched a number of years ago now. I actually went to a launch party for it. That's how cool I am. Not the launch party with the rocket. Like, I wasn't there to see it lift off. It was just in our department at the university. Anyway, it takes images that look a bit like this. Each pixel in this image is 30 by 30 meters. So it represents a 30 by 30 meter area on the ground. And you get a new image from Landsat every 2 weeks. So you can look at change over time. This is Southampton, where I live. This is an alternative satellite called Sentinel-2, slightly higher resolution. Can anyone tell where that is? Yep, that's EMF. That's last year's EMF. I decided not to try and get an updated one for this year this quickly, but this was not last year, sorry, 2 years ago. You can see the stage A in red and stage A in purple and stage B in red and so on. So we've got these things from satellites, and satellites have sensors on them that are very similar to these spectrometers, but they're a bit simpler really. They use filters on them to get a wide range of wavelengths into one measurement. Rather than taking a measurement at every wavelength, they just take it at some wavelengths. So here's our nice spectrum from our lamp. If we put a filter under it, it just cuts off some of the light. So this is a red filter. It's roughly the Landsat red band wavelength, so we just cut off the light there. And then we say everything else we've got here we'll measure as one number and call that the red measurement. So if we do that, we get graphs a bit like this. We can look at different things on the Earth's surface, different land covers we call them, and look at where they plot on a graph with these different wavelengths. So here we've got about 5 wavelengths being measured. We've got a couple of blue, a green, a red, a near infrared, and a couple of other infrared ones. And we can see a shape on the graph. This is the shape you would get if you were looking at forest. If you were looking at a farmer's field, this is the shape you would get. You'd see you're getting the same pattern, but shifted up a bit brighter. And that makes sense. If you're flying in a plane, a farmer's field, like pasture field, looks brighter than a forest or whatever. You'll notice those are also very similar to the patterns we were seeing earlier on the spectrometer. We've got this low blue, higher green, low red, and high near-infrared reflectance like we were seeing from leaves down here. And we can put some other things on it. So urban looks a bit similar to what we were seeing from the tarmac. It's kind of gradually increasing across the wavelengths. And I was going to demonstrate water here, but I couldn't get the depth of water to work, enough depth to make it work here. But water has some reflectance in the blue, as you'd expect, and then really drops off to almost zero as soon as you get towards the infrared. Now, these patterns here are known as spectral signatures, the same sort of patterns that we see when we put things under the spectrometer here. And we can apply a very simple algorithm to use these to classify what we're seeing in our satellite images. So we look at every pixel in the satellite image, and we say, which of these graphs is it most similar to? Does it most match the forest one, or does it most match the water one? If so, say it's forest, or say it's water. And we get maps like this. So this is an automatically created land cover map from satellites. This is a European-wide one called Careen. You can see urban areas in red, you can see forests in green, you can see water in blue, and so on. We can also get even more detailed. This is using European Space Agency data at 10-meter resolution. And that means you know what's on the ground for every 10 by 10 meters in the entire world. You don't have to trek to the middle of the Amazon rainforest to find out if there's anything else there. You can see which bits are trees, which bits used to be trees and are no longer trees, and so on. And if we zoom in to this area, this red bit on the edge here is the urban area, although I use that term lightly, of Ledbury. And the little tiny bits of blue here are the lakes within the EMF site. The EMF site is about here. So that's really powerful stuff you can do with a spectrometer. But you can also, with a satellite which measures in the similar way to a spectrometer. But you can also do other stuff. So let's take one of these leaves off again, and we'll switch back here, and we'll do a reference measurement. Here is a healthy leaf. Let's just get that working a bit better. Whoops, let's do another reflectant, another reference. And so here's our healthy leaf. So we've got high green reflectance, high near-infrared reflectance, low everything else. Let's take a slightly less healthy leaf. This one I put in a bag a few days ago. The whole thing is a lot lower. The whole thing is reflecting less well, and there's nowhere near as high a near-infrared reflectance. And we can take something like a really old leaf. This leaf is so old it's brown, and we will see that we get a completely different spectra with no peak in the green and not that levelling off in the near-infrared. So just to compare the few, here's one, and here's, where did it go? Here's, whoops, that's the wrong one. Here's the other, and here's the brown one. So you can see that they look quite different, and we can start to see that different things are happening with these leaves. Now we can, in fact, quantify what's going on here. What we're getting here when we've got a leaf that is less healthy in some way, so maybe it's stressed, it hasn't got enough water or enough fertilizer, or it's been plucked off its plant, or the plant is dying. We get lower green reflectance, we get lower near-infrared reflectance, and we get this what's called blue shift of the red edge, where something there just kind of moves, the big peak moves a bit. And we can kind of see that here. We've got a change in those reflectances. And there's a way we can measure this in a very simple way to look at the health and density of vegetation from things like satellite images. And it's called the Normalized Difference Vegetation Index, or NDVI. What we do is we take the amount of near-infrared light, subtract the amount of red light, then take the amount of, divide it by the amount of near-infrared light plus the amount of red light. So let's have a look at that. Let's take a reference spectrum and then look at our healthy leaf that I've just taken off a live plant. So if I press this button, we will see what Landsat sees from a satellite. So rather than seeing all these individual measurements on the red lines, it will see these sort of 5 or so black points that are connected by the black lines there. So it's only getting a few wavelengths measurements. But then we can put on an NDVI output, and we can see that our NDVI for this leaf is about 0.81. Now this is the moment of truth to see whether this behaves the way it should do, the dangers of live demos. If we put this leaf on here, we see we get an NDVI that's lower. This is a less healthy leaf, it's been detached from the plant, it's gradually dying, and that's an NDVI of 0.7. And if we put our completely dead leaf on there, we get an NDVI of about 0.5. If you put something like water on here, you'll get an NDVI of -1. The other interesting thing is we've got something here which is a fake leaf. This is just a plastic leaf, and it looks like a leaf, obviously, to us, but you put this here and you can see you get a not bad NDVI, in fact, but you get, everything's very much lower than you would expect, and the near-infrared really isn't peaking in the way you would expect it to. So, first, can I have my glamorous assistant? This is my wife who's going to be my glamorous assistant. Can you set up the retort stand? Oh, we're getting a round of applause for my glamorous assistant. Thank you very much. So, while she's doing that, yeah, get that there, and yeah. So while she's doing the setup, I'm going to talk a little bit more about NDVI. So you can apply that measurement, that NDVI calculation, to every pixel in a satellite image and look at NDVI over the whole of your image. So this is a satellite image over Southampton showing NDVI. Red is low NDVI, green is high NDVI, and you can see quite a lot of interesting patterns. Sorry? Here. You can see quite a lot of interesting patterns. Yep. So you can see that there are some fields that are red, so they're not growing vegetation. You can see some fields are very dark green, they've got very healthy or very active vegetation in them. You can see some fields have patterns in them showing less vegetation in different areas. If we zoom in, we can see a farmer's field here. The top farmer's field has no vegetation in it. Bring it back a bit. The middle field has vegetation in it, but it's not growing actually as healthily as the vegetation in the hedgerows and so on at the side, and it's got patterns in it showing different health of vegetation across the field. Right, we're going to switch now to, can you grab that? We're going to switch now to looking at something that's a bit more chemistry related. So, let's just get this. There we are. So this, what I've got here, we can switch to the camera on the stage if you want, just to see the setup here, if anyone can do that. You can just about see it. So here we've got our halogen lamp, which is pointing at our integrating sphere to get a nice uniform bit of light coming out of the integrating sphere. Then we've got the spectrometer here, and we've got a test tube of water in between the spectrometer and the integrating sphere. And what we're seeing through this water is basically the same spectrum that we would see from the light without the water. I can take the light without the water away. The numbers change a bit, but the pattern doesn't. That's because... Oh, sorry, can we switch back again? Sorry. There we are. So if I take it away, it doesn't really change what you can see there. That's because water is transparent, as you've probably noticed. What we're then going to do, though, is put some other stuff into this water. Now, I looked far and wide for chemicals I could use to do this that EMF wouldn't shout at me for using on stage, that my wife wouldn't shout at me for using because I might hurt myself, and so on. And I decided to use blue food colouring because it's very safe. So this is putting some blue food colouring in here. Whoops, that's just fallen off. That's because I knocked it. There we are. So what we're going to do is put some blue food colouring into this water, and we'll just keep that spectrum at the top there to begin with, and we'll put a bit of blue food colouring in and stir it up a bit. This is a tiny bit. The water barely looks blue at all, but we can see there's this big dip in the middle of our graph. The blue food colouring is absorbing light at a certain wavelength. If we put a bit more in, oh, that's a bit more than I intended, and stir it up, we can see we get an even bigger dip. If I put even more in, we can see we get an even bigger dip. And basically, the depth of this absorption feature in the graph is proportional to the amount of blue food colouring I put in. So if I was a chemist wanting to find out the concentration of a particular substance in this test tube, I can use this sort of approach to work out the absorption features due to a particular chemical and reverse it to work out how much of that chemical I have. Now, we can also do the same thing with things in the atmosphere if we're trying to measure those from satellites. So, for example, this is a measurement of light coming from the sun through the atmosphere. All these little dips you can see here are absorption due to various things either in the sun's atmosphere or the sun itself or in the Earth's atmosphere. So this massive dip here is because of oxygen in the Earth's atmosphere. There's an absorption feature at 760 nanometers. If you don't see that in your data and someone purports to have measured it on Earth, then they're lying because there is always oxygen in the atmosphere on Earth. But you can see all sorts of other things due to hydrogen of different types, sodium, all sorts of things that you find in the sun or the Earth's atmosphere. And we can do some simulations of this with something that we might actually want to measure, because we kind of know there's oxygen in the Earth's atmosphere and the exact concentration doesn't change that much, but other things do. So this is a simulation of what you would see at a satellite from a reflectance of a vegetation spectrum again. So this is the low blue, high green, low red, high near infrared thing. And we put some atmospheric effects in there, and if we just ignore what's going on the left here for the moment, we'll come to that in a moment, we get this big dip because of oxygen in the atmosphere. But then we put some water vapour into the atmosphere, and we start seeing other dips, mostly outside of the range this spectrometer can see, so I can't really demonstrate that. And then we put some more water vapour in the atmosphere, and we get bigger dips, and even more water vapour, and we get even bigger dips. So then all we need to do, and I say all we need to do like it's super easy, people have spent their careers doing this, is measure the depth of this dip, and you have a measurement of water vapour, and the amount of water vapour in the atmosphere at the location you took that measurement. So we can do this from satellites, and we can do it with other things than water vapour. So one thing people are interested in is air pollution. Nitrogen dioxide is a potent air pollutant. It's bad for human health, amongst other things. And you can measure that from satellites by looking for these absorption features. So on the left here, we've got nitrogen dioxide across Europe. You can see concentrations for Paris, London, the Low Countries. The Po Valley in North Italy is very polluted because there's a lot of pollution that gets trapped there and can't get across the Alps. The right-hand image is the same, but taken during the COVID lockdowns. So you can see the big difference in pollution there. The other thing I want to demonstrate, and this is the bit that's a little bit experimental of my talk, but we'll see how we do, is emission spectra. So there we were looking at what happens to light when it goes through something. Here we're going to look at what happens to the light coming from something. So I have some normal tea light candles here, and I'm going to put my tea light candle down there, and I'm going to light it. I did get permission to use candles on stage. That's why people have got flamethrowers here. The candle is really nothing. So let's have a look at the spectrum. We have to get this just about right to not burn it, but point it at the right thing. Oh, that's showing like it's contaminated already. The problem with this is the thing I'm going to demonstrate in a moment tends to contaminate anything that you find. Let's just let that burn for a second. There we are. Take it while it worked well. So there's a spectrum of the candle. So this is the light coming from the candle. It's a kind of orangey, reddy light, so that's why it's peaking in the orangey, reddy part of the spectrum, and it looks fairly normal. We're then going to take another candle that I have contaminated with a mystery substance. No. Thank you. Not food colouring either, in fact. So here is a candle that I have contaminated. Let's light that. Whoops. There we are. And let's just get... Oh, it's gone out. Of course it has. Let's go back to the previous candle and contaminate it live on stage. Right. I don't know where my teaspoon has gone, but never mind, let's just pour it on here. So I've got a mystery substance here that I'm going to put here. Whoop, oh, now I've blown it out again. Apologies, never do live demos. Right, let's just let that burn a second, and we'll point this. Nope, okay, that's not working. One last go, and then I will tell you what I was expecting to see. I said this bit was experimental. Right, here we are. Right, let's just get that pointed there. Can you see that what we've got here is a couple of really big peaks in the wavelength spectrum that you wouldn't normally see from a candle. The candle you would normally see earlier was this broad spectrum in the kind of reddy orange area. We've got two big peaks. We can find out what wavelength is they're at, so that's at 588-ish. This one is at 766, and you can go off and look those up in a chemistry data book, and you find that one of those peaks is for sodium, and the other one is for chlorine, and so I've got sodium chloride, which is table salt, which I've put on my candle there. And you can do the same thing with all sorts of other things that emit light. So linking this to the space theme of EMF, some elements were actually discovered extraterrestrially before they were discovered on Earth. So we first discovered helium by seeing an emission line, so this big peak of emission from the sun that we didn't recognize for any substances on Earth. And they named it helium after the Greek god Helios, and then eventually found it on Earth and purified it and experimented with it on Earth. So, I've just been told I've got 1 minute left. That's absolutely perfect because this is my last slide. And all I want to say is there's loads more stuff we can talk about this. There's a whole angular dimension that I haven't even mentioned. Vegetation, for example, reflects very differently if the sun is there and the sensor is there to if the sun is there and the sensor is roughly where the sun is. So there's a whole angular thing going on. There's a whole thing I wanted to demonstrate about aerosols in the atmosphere and how they scatter light, and they do it at different wavelengths. I had a whole thing with incense sticks to try and do, but it just wouldn't work reliably in a non-lab setting. There's a whole load of stuff we do with satellite data to try and correct for those sort of atmospheric effects, things like the scattering and the absorption of light by things in the atmosphere. And there's whole other things to look at, different sorts of vegetation, different sorts of lights, and so on. So if you want to have a play with any of this, come to the Q&A tent. I'll bring my kit. I don't think there's power there, so we won't be using the lights, but we've got a big sun that we can use as a light source, luckily today. So we will use that. Thank you very much.